Okay, in this section we're studying so-called combinations, and before we get into combinations, I want to remind you about permutations. So if you have n objects and you grab r of them and line them up in a line, there are n factorial over n minus r factorial many results that you could have. And we're going to do a similar procedure to starting with n objects and grabbing r of them and doing some count with that, but it's going to be slightly different than lining them up and asking about the different possibilities. So imagine that you have a deck of cards in front of you. I'm going to use the set deck because just for variety. So we've got 81 cards in our set deck, and I'm going to imagine just reaching in and grabbing 3 at random and seeing what cards I get out. I'm not selecting the cards in sequence, and the order really doesn't matter. I'm just really grabbing 3 at random and asking about the total possibilities that I could end up with. So I've got the set deck over here, and maybe I'll do like a possibility tree to imagine the results of this selection. So I could imagine selecting a first card, then a second card, and then a third card just to organize my thoughts. But remember, I don't really have a first, second, and third place. I'm just at the end trying to grab 3 distinct cards. So I have 81 possibilities for the first card, right? So I can imagine, okay, drawing 81 branches on that first stage. And then once I've made the selection of that card, let me just choose. Once I've made that selection, I only have 80 left. So imagine I grab that out of the deck. I only have 80 cards left. So let me grab another one. And at that point, I only have 79 left to choose from. Oh, unfortunately, I didn't grab a set, but whatever. So this is one of the possibilities that could result from this selection. Again, growing my possibility tree here, there are 81 possible first cards, and to each of those, there are 80 possible second cards, right? There's no way I'm going to be able to draw that branching in any reasonable fashion. But at the sort of third and final stage, I have 81 times 80 many possible paths, and to each one of those, there are 79 selections of the last card. So it appears at first glance that I have 81 times 80 times 79 possible 3-hand selections. But let's look at the problem that occurs here. So I have whatever that number is. Maybe I'll compute. Okay, so what I have just computed here is the number of lineups of length 3 from 81 cards. So that's the number of permutations of length 3 from 81 cards. Okay, so this isn't the right count though, because the order sort of is implicitly mattering when I set it up like this. So let me try and convince you why this is just way, way too many. Is it going to let me shrink these at once? No, it won't. Okay, so over here in the possibility tree, there are 511,920 leaves to the tree, okay? And each of the paths or branches through the tree represents, selecting these cards one by one. So this is one outcome that you would see over there on the far right. Well, you would also, on a completely different branch, see the following possibility. As an outcome. So the first branch that was followed to produce this was the double squiggle, the red double squiggle solid card. The second card was this one, and the third card was that one. That's a completely different branch in the possibility tree, and so these 2 outcomes were counted separately. And as far as grabbing a 3-card hand where I don't care about order, I don't want to count these separately. These are actually considered the exact same outcome. And so how many overcounts is this hand getting? That's worth thinking about, right? Well, I'm going to get an overcount of all the possible ways that I can arrange these 3 cards. So I'm drawing a couple of these arrangements, but think about it. How many arrangements of these 3 cards are there? And they're going to represent, as many different repetitions of the leaves of the possibility tree. All right? So how many ways can you arrange these 3 cards? Well, that is exactly P33. That is saying arrange 3 cards from 3. And that is 3 factorial over 0 factorial, which is 6. So these 3 cards are represented in 6 different hands in the possibility tree. But it's not just these 3 cards that are special, right? Every single hand of 3 that you construct in this way is repeated in the possibility tree exactly 6 times. So this number right here does represent the number of ways to line up 3 cards selected from 81. But if you just want to grab 3 cards from 81, not caring about the order, then you're going to have to compensate for the overcounting. So actually, some books indicate this as C81-3, and it's going to be the count that we had before, but then dividing out all of the repetitions. So every single set of 3 cards has been overcounted in this way. There are 6 occurrences of each of them. And so if I divide by 6, then I get the correct count. And this is 85,320. So let me come back over here and summarize what I did to count. So to get this count, I took 80 times 79, and I divided it by 6. And as a reminder, this 81, 80, 79, this was written back in the permutations section as 81 divided by 81 minus 3 factorial, which is 78 factorial, right? That's what the top is. And then here, in this case, I have an extra 6, which is 3 factorial. So this is the correct count of choosing 3 cards from 81 when we don't care about the order that those cards are chosen. All right, so we've got actually a couple different options for notation here. The one I prefer is this right here, a set of parentheses with 81 on top and 3 on the bottom. But as I said before, some books use this, 81, 3. So P and R is a way to express the number of permutations. C and R is the way of representing the number of combinations. So this is the number of size 3 combinations from 81. And we also read this notation as 81 choose 3. Okay, and it just ended up being this computation here, 81 factorial divided by 3 factorial, and also divided by 81 minus 3 factorial. Okay, what about grabbing a 4-card hand from the set deck? The count would go much the same way, right? You would start by creating a permutation of 4 cards. So you'd have 81 choices for the first, 80 choices for the second, 79 for the third, 78 for the last, and you'd realize that you did an overcount because any one of the 4-card hands would be overcounted 4 factorial many times. So to compensate, you divide by 4 factorial. And of course, at the end of the day, what you're looking at is this computation. Okay, so this is also read as the number of ways of choosing 4 items from 81, or the number of 4 combinations from 81. Okay, so in general, as I mentioned before, if you have a number of objects n and you grab r of them, then that's called an r combination. So you got n cards in your deck or whatever, and you're grabbing R of them at random, then there are n choose R many outcomes. So this is the symbol for n choose R, and our computation is exactly as we sort of discovered in our particular examples. Okay, so let's go ahead and use this new notion of the number of ways to choose R items from n to do some computations. So suppose that you have a set. You don't know what's in that set. All you know is that there are 25 things in that set. So you could even imagine A is like actually being the numbers 1 through 25 if you want. But A has 25 elements inside of it. And then I want to find, let's parse this expression here. I want to find the cardinality, so the number of elements in this set right here. What is this set? This is a set of subsets of A that they themselves have cardinality 6. So for example, if I was to try and write out this set, then one of the B's that would be present in it would be, for example, 1, 2, 3, 4, 5, 6, right? And then another B set might be 25, 24, 10, 9, 8, 7. That's another B set. And then there's many others, right? Just sort of talking about what we have here, the entire collection of subsets of A would have 2 to the 25th many elements in it, right? The cardinality of the power set of A is 2 to the 25. But this isn't the full power set, right? I'm just looking at very specific subsets of A, only those subsets that have cardinality 6. How many are there? Well, constructing a subset of A that has cardinality 6 is like grabbing 6 elements at random from the set of 25 elements in A. So this is going to be 25 choose 6. It'll be 25 factorial divided by 25 minus 6 factorial, which is 19 factorial, times 6 factorial. Okay, I don't particularly care about computing these things, but if you have to, do some reduction first. So like I like to cancel the biggest factorials that I can. So we can go like this. And then write out the bottom. So I canceled the 19 factorial, and then you can write this out. And then you can do some cancellation further. Like this cancels with that, and then this leaves an 11, and then this cancels with that. So you can do some of this stuff by hand. All right, so I'm left with whatever this number is, right? And like a handheld calculator will deal with this much easier than it deals with 25 factorial or something. So whatever this number is the answer to the question. 25 choose 6 is exactly the number of cardinality 6 subsets of a set of size 25. All right, let's answer a similar question. So I got that same set of 25 elements, that's a set A, and I want to gather together all of the subsets whose cardinality is less than or equal to 3. Again, let me just try and take a look at this set. The empty set is a subset of A whose cardinality is less than or equal to 3, right? Its cardinality is 0. Singleton 5. Yep, that's a subset of A that has cardinality 1. And then you have like 1, 10, 24. There's another set whose cardinality is less than or equal to 3, and so on like that. Well, it's going to be convenient to split up this count into, I think, 4 pieces. So let's write this set as the union of, I think, 4 different sets. All of the sets that have cardinality 0, all the subsets of A that have cardinality 1, all the subsets of A that have cardinality 2, and all that have cardinality 3. That way I split this problem up into basically 4 of the previous problems I had. Okay, so how many subsets of A have cardinality 0? Well, just one. That's the empty set, right? And then, actually, I don't want to try and list these out. I'm just going to do the counts here. So let's go like this. The cardinality of this is just going to be, well, there's one set that has 0 elements. That's the empty set. How many subsets of A have cardinality 1? That's all the singleton sets, right? And A has 25 elements in it, so that is going to be 25 singleton sets. You can write it in terms of choose, though, right? If you have 25, choose 1, that is gathering together all of the 1-element subsets from the set of cardinality 25. And then over here, what are all the how many subsets of A have cardinality 2? Well, that's the count of taking 2 elements from 25, choosing 2 elements from 25. And then finally this right here. So whatever this count is, we don't need to expand further if we don't want to. Let's see how we can use this, n choose r in different counts other than just like grabbing subsets from a set. So I've selected 3 names of professors in the math department, and I am trying to count the possible arrangements of the letters. So like take the letters in Professor Watson's name and arrange them in different orders. So we could say A, T, N, W, O, S. Did I get them all? Yep. Or T, S, O, W, A, N, and so on. What are the possible different ways that I can sort of permute these letters? It's actually a permutation. The number of different ways is going to be 6 factorial. You've got 6 choices for the first letter, 5 choices for the second letter, 4, 3, 2, 1, and so on. There's 6 factorial. Okay, now let's move to my last name. I've got Yengulalp. There's 2 L's, and that's actually going to change our count slightly, right? And here's why. Got 9 letters in the last name. 1, 2, 3, 4, 6. Ugh, did I get them? Yeah, 9 letters. And we start with 9 choices right here, right? Because there's 9 letters that I have over here. And then I move on and I have 8 choices, 7 choices, and so on. But here's a problem. Since there's 2 L's, and with the count of 9, 2 of them are, counting as 2 of the 9, choosing the first L is no different than choosing the second L. So for example, if I chose an L for the first letter, maybe that one, and then by the time I got to this position, I chose the other L, right, to place that one, then that would have the exact same look, the exact same, resulting permutation as if I had chosen this L, which is another one of the 9 for the first space, and this L for this space. So I have overcounted the number of permutations if there's a repeated letter in my, name. So here's what we do first. We count the number of arrangements in a sequence of steps. First, we place the L's. I'm going to write L like that so you can tell it's an L and not an I or something. And then we're going to place the rest of the letters. And I'll use the multiplication principle as I do this. So step number 1 is going to look like this. I've got 9 spaces to put letters. I'm going to choose 2 of them to place the L's. So choose 2 places. All right, so let's say I put an L here and I put an L there. All right? There are how many ways to do that? Well, there's 9 spaces, and I'm going to choose 2 of them to place L's. So the L's go in, and then all the rest of the letters are distinct. So I have, let's see here, 7 choices of what to put there, 6 choices of what to put there, 5 choices to put there, and so on. And since there's no repeated letters, I don't have the problem I did with the L's in the first place. So placing the rest, there are 7 factorial many ways to do that. So the answer, so the possible arrangements of the letters in the name Yangulelp is 9 choose 2 times 7 factorial, whatever that number is. Okay, let's move on to Professor Wesselcouch. We have a repeated C and a repeated E. Anything else? I think that's it. And a total, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. Okay, so step number 1, we're going to place the E's. Step number 2, we're going to place the C's. And it doesn't matter in what order I do this. We'll get the same count. And then place the rest. Okay, so how many ways can I place the E's? There are 10 slots to place letters, and I am choosing 2 of them to put the E's in. Once I've done that, I only have 8 slots left, and I'm going to choose 2 of them to put the C's. And then placing the rest, all the rest of the letters are distinct, W, S, L, O, U, and H. So I have 6 factorial, many ways to do that. Applying the multiplication principle, the answer then is this. Okay, so that's a fun little exercise of mixing the n choose r count with some other like kind of multiplication and permutation principles together. Okay, let me remind you what a standard deck of cards looks like. You have 2 red suits, diamonds and hearts, and then 2 black suits, clubs and spades. And then you have 13 different numbers that the cards can take. So you've got 2, 3, 4. Okay, so 2, 3, 4, all the way up to 10, Jack, Queen, King, Ace, like that. So that makes a total of 4 times 13 many cards in the deck, which is 52 cards in the deck. So let me just draw like one of these cards so you understand what I'm talking about. There is a card in the deck that is a jack of hearts, a jack of diamonds, I guess. So you've got a jack and diamonds. Like this. Okay, and here is a 7 of clubs. Okay, and I don't expect you to be familiar with like poker or anything like that. Just Google any term that you need to that's used in like counting with standard decks of cards. So when you're playing like 5-card draw or something like that, you grab cards from this deck of 52 and then you take a look at what you got, and certain hands are worth more depending on what you're playing. So a flush is a poker hand that has cards of all the same suit. So you grab 5 cards from this deck of 52, and if they are all hearts, then you're in business. So heart, 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 heart. And it doesn't matter what the value is up here. It could be anything. So a 1, a jack, an ace, a jack, a 6, a 2, and a 10, or something like that. That would be considered a flush. So let's try and find the number of flushes in the deck. Well, I'm going to do it in a 2-step process. I'm going to first decide which suit, and then which cards. So which suit? Well, there are 4 suits. And which cards? Well, there are 13 cards of any particular suit, and you're grabbing 5 at random. So that would be 13 choose 5. So the answer to the question would be 4 times 13, choose 5. Again, whatever that number is. And you might say something like, I should probably, as we're doing these counts, insert probability questions in there. So you can ask a similar question saying, what's the probability of drawing a flush? Well, what you're going to do is you're going to take the number of flushes that there are possible and divide it by the number of 5-card hands. Well, a random 5-card hand is just 52 choose 5, right? So this measurement divided by this measurement will give you the probability. This is like 0.002. So it's like a 0.2% chance. Okay, what about a 2 of a kind? 2 of a kind means out of your 5 cards, 2 of them have the same value. So you might have, for example, a jack of spades. Oh, I started drawing a clubs. Let's say jack of clubs and a jack of diamonds. That would be considered a 2 of a kind. So I'm going to count the number of different two of a kinds I could come up with into a 3-step process. First, I'm going to decide on the value, like I had decided on jack here, and then I'm going to say which 2 jacks appear. So once I've decided on jacks, it could be clubs, diamonds, hearts, spades, diamonds, whatever. And then after that, I'm going to choose the rest of the 3 cards. And I have to be careful because I don't want to allow more jacks when I go and choose the last 3 cards. Let's do these counts one by one. Which value do I want? There's 13 possibilities. And then of those, like however many cards have that value, there's just 4 of each value. Which 2 are you going to choose? Well, that's 4 choose 2, right? Okay, so to choose the remaining 3 cards, you have to be pretty careful not to make another pair or make this pair into a 3 of a kind or a 4 of a kind or something like that. So what we need to do is, of the 12 remaining values in the deck that aren't the one that I chose to make the 2 of a kind from, I'm going to choose 3 distinct values. So step number 1 is to get, of the 12 leftover values, 3 of those. I'm choosing 3 distinct values here so that I'm sure that I'm not making another 2 of a kind. And again, I'm not choosing that first value of jack that's in the picture to accidentally make this 2 of a kind into a 3 or 4 of a kind. So I do that. I decide on what other values I'm going to do. Like let's say something like a 7 and a queen and an ace or something, all right? And amongst those, I'm just going to choose the suit for each one of them. It doesn't really matter what suits I choose. I got 4 choices for the 7, 4 choices for the queen, and 4 choices for the ace. So that's 4 times 4 times 4 remaining. This together gives me the number of hands that only have like 1 2 of a kind, or a pair it's called. So that's 13 times 4 choose 2 times 12 choose 3 times 4 cubed. Next to a 3 of a kind. So let's imagine our 2 of a kind being jacks, and then I'm just going to make some 3 of a kind, let's say from 2s. So let's say 2 of hearts, 2 of diamonds, and maybe 2 of spades. Okay, so this is a full house. The way I'm going to count the number of full houses that there are, I'm going to, choose the 2 of a kind, and then choose the 3 of a kind. Okay, choosing the two of a kind goes much the same way it did a second ago. I first decide on the value of the two of a kind, and then I choose two of those cards. For every single way I can make a two of a kind, I now have to decide on the three of a kind, right? Well, how many suits are there, or pardon me, how many values are there left for my three of a kind? I chose one of the 13, and so there are only 12 left. If I allow it to be the same value, there's no way I'm going to get a two of a kind and a three of a kind of the same value because there's only 4 cards of that value. So there's 12 choices there. I've chosen 2 in my picture. And of those 4 cards, I need to select 3 to make the three of a kind. So here I did spades, diamonds, hearts, but I could have done hearts, diamonds, clubs instead. So there are exactly 4 ways to do that. That's 4, choose 3. Okay, there is the count of the number of full houses.